Okay, let's dive right into this explainer. Today we're tracking down a really thrilling, centuries-long philosophical mystery. Basically, we're looking at why humanity constantly feels the need to chop up fluid, continuous ideas into rigid little boxes. It's this fundamental, almost obsessive drive that shaped our ancient history, structured our legal systems, and right now, it's literally defining the hardware powering modern artificial intelligence.
I mean, just think about human imagination for a second. It's completely fluid, right? It's this continuous, unbroken stream. Our thoughts just flow naturally. We associate one idea with the next without hitting any hard boundaries. A thought doesn't just snap perfectly to a grid. And yet the systems we build to contain and share all that imagination, they are almost entirely rigid, chopped up and highly structured. So why is that? Why do we constantly force our continuous, messy reality into discrete, manageable little blocks?
Well, to answer that, we have to look at a massive historical pivot that happened right around 500 AD. Before this, the dominant format for storing information was the continuous Roman scroll, and it beautifully mirrored that unbroken, flowing nature of thought. You just rolled it out, literally a river of text. But as society got more complex, especially with all the intricacies of Roman law, we suddenly needed exactness. We needed to be able to point to a very specific rule at a moment's notice. So we completely abandoned the scroll for the segmented, paginated codex. We essentially traded the river for a bounded container just to lock down meaning and make specific ideas immediately locatable. And that shift from the scroll to the codex, that was really just the beginning. It kicked off this relentless, multi-century drive toward quantization. It's our absolute obsession with chopping the continuous world down into smaller, manageable, discrete units. Whether we're dealing with thousands of pages of ancient laws, vast digital libraries, or even the complex mathematics firing inside modern processors, our instinct is always exactly the same. Chop it up so we can scale it up. To really see this in action, imagine you're a monk in 12th century Bologna. The university there is absolutely booming. Thousands of students are flooding in, and every single one of them desperately wants a copy of Justinian's massive legal code. And you, sitting at your desk with a quill, are the bottleneck. Sitting down to copy thousands of complex pages by hand, cover to cover, one letter at a time, was an absolute logistical nightmare. The demand was just exploding, but the analog output of a single human hand simply couldn't keep up. So, to bypass this nightmare, the university invented something totally ingenious. They called it the Panaccio system. They essentially took an authorized, error-free master textbook and quite literally shattered it into bite-sized, standardized chunks called panacea, or pieces. So instead of one poor monk trying to tackle this massive book all alone, they rented out these individual pieces so dozens of professional scribes could copy the exact same book simultaneously. It was the ultimate modular workflow. They took a massive continuous task and broke it down into perfectly sized blocks. So the absolutely crucial takeaway here is that these 13th century scholars essentially invented a massive parallel processor. By breaking a continuous text into discrete modular chunks, they dramatically scaled up the speed, the volume, and the accuracy of text reproduction across all of Europe. Honestly, it wasn't just some slight operational improvement. It was a complete masterclass in workflow management that fundamentally changed how human knowledge was distributed.
Okay, fast forward to 1981. The technology has completely changed, obviously, but the fundamental human bottleneck, exactly the same. As early computing started to absolutely explode, computer scientists realized a major problem. They couldn't just feed a continuous, ambiguous stream of human language into a machine. They desperately needed a way to quantize the digital word so that a totally deterministic, rigid computer could actually process it, search it, and store it efficiently. And that brings us to a massive paradigm shift, spearheaded by a guy named Charles Goldfarb. He created SGML. Goldfarb basically figured out how to break down digital text to completely isolate its core semantic meaning from how it physically looked on a screen. Think about the gravity of that for a second. Goldfarb was doing to digital documents exactly what the Pasea system did to those medieval law books. He was breaking them down into strict, highly manageable pieces. He pulled this off by strictly separating descriptive markup from procedural markup. So instead of giving a computer a procedural command, like, make this text bold, you give it a descriptive label that says, hey, this text is a title. By making that switch, Goldfarb turned fluid, ambiguous human language into a highly structured, machine-readable meta-language. He literally took the flowing river of words and locked it firmly into a totally discrete, predictable grid. Now, what if we apply that exact same chunking philosophy to modern hardware? Well, that is exactly what's happening right now with the high-performance GPUs that are powering our current technological revolutions. Enter NVIDIA's Tile IR. Traditionally, if you wanted to program a GPU, developers had to meticulously manage incredibly low-level hardware details. We're talking individual threads, crazy complex memory hierarchies. It's notoriously difficult. But Tile IR completely abstracts all of that away by modeling the GPU as a tile-based processor. It takes multi-dimensional arrays, which you can sort of think of as incredibly complex 3D spreadsheets, and it chunks them into manageable, discrete data blocks called tiles. This is a real game changer. It allows programmers using tools like the new Qtile package in Julia or Python to focus purely on high-level data chunks. The compiler just automatically maps these tiles directly onto the hardware resources. Think about it. If you're a programmer writing Python today, you're dynamically distributing discrete tiles of data to parallel GPU cores, which perfectly mirrors how that medieval Pasticcia system distributed discrete pieces of parchment to parallel scribes. It's the exact same architectural solution to scale human effort, just centuries apart. Crazy, right? When we map all this out, the pattern is just undeniable. Text moves from ancient continuous scrolls to rigid SGML tags. Law shifts from fluid oral customs to quantized Polysia chunks. Technology transitions from analog human thought to highly structured tile IR GPU processing. I mean, we even see this in business. There's this constant clash between long-term organic value creation, like patiently growing a vineyard over a decade, versus liquidator models that just extract and discretize that value for short-term gains. The human drive to extract, chop up, and discretize the world is absolutely everywhere. But here's the catch. Forcing fluid concepts into rigid boxes isn't always smooth sailing. Today, especially in the era of massive large language models, this rigid grid is finally starting to crack under the pressure. When you try to force the infinite messy complexities of human language into tiny mathematical boxes, you hit a massive friction point. The real issue here is that AI algorithms, using methods like byte pair encoding, are forced to arbitrarily fracture continuous human concepts into discrete numerical chunks just to process them. Take a continuous mathematical concept like the number pi, for example. To an AI, pi isn't a singular, holistic idea. The tokenization process literally shatters it into completely arbitrary subwords, a 3, a decimal point, a 14, and a 159. This kind of arbitrary fracturing creates a severe modality gap. It makes what should be super simple, logical arithmetic, incredibly fragile for these multi-billion-dollar models. And this tension right here, between the fluidity of human thought and the rigid digital chunks we keep forcing it into, leads us to a really fascinating turning point. We kind of have to ask ourselves, is modern AI finally helping us break free from these discrete bounds? Are we actually starting to return to our ancient, unquantized roots? Consider the legendary author Jack Kerouac for a second. He notoriously hated discrete, paginated paper. In fact, he actually taped his pages together so he could write his masterpiece On the Road in one continuous flowing scroll. He did that precisely to capture the raw, unbroken associative magic of human bot. Well, today, we're seeing modern AI command line interfaces doing essentially the exact same thing. By streaming words sequentially back to the user, token by token, they mirror the continuous flowing nature of a human pouring thoughts onto a page. It creates this highly visceral connection, almost like watching a typewriter streaming onto a scroll, rather than just dumping a pre-rendered static block of text all at once. So, what does this all mean for us? We've spent literally centuries chopping up our world. From the codex to the pager system, from SGML to tile IR, we built a highly discrete, rigid grid to manage and scale complexity. But as our interfaces become more continuous again, streaming language like a natural conversation, we're left with a huge question. Are we finally done chopping up our world? Are we finally leaving the grid behind to reunite with the flowing river of human thought? Thanks for joining me on this explainer, everyone. I'll catch you next time.